So this is fine. It looks like this is just a straight review of the AP Calc, and that's cool. Okay, you want to start on this first problem here?
Yes.
Calculator active, okay. So we're looking at the graph of the derivative, and it's piecewise. And they don't tell us what the first function is that looks like a semicircle.
Yeah.
They do tell us the second function, which looks proper. Okay, the graph of the continuous function shown in the figure, okay. And they tell us it's a semicircle, and that f of 0 equals 5. Alright, inflection points. Where does a function have inflection points?
Aren't the inflection points when the derivative equals 0?
It's when the second derivative equals 0.
Equals 0.
Yeah. The first derivative equals 0. In other words, you know what? Let me put this up here, because this thing is so valuable, I hate to not show it. Now I can just make sure I know where it's at. What we have here is the function, its first derivative, and its second derivative. Let's just review. When the function is increasing from there to there, can you see my mouse?
Yeah.
The first derivative is positive, right? The first derivative is decreasing, but it's still positive.
Yeah.
Okay. When the function is decreasing, the first derivative is negative. And when the function is increasing again, the first derivative becomes positive again. Which means when the first derivative is 0, that point and that point, it means that the original function has horizontal tangent lines, which it does. And horizontal tangent lines are critical because they represent when the original function has a local maximum or a local minimum. And that is the real-life problem that we're always trying to solve, is where is the maximum of a function, or where is the minimum of a function? Well, if we can take the first derivative of a function, set it equal to 0, we've found that spot. In other words, if we take the first derivative of that function, set it equal to 0, we find that spot and that spot. And that is a local maximum and a local minimum. Well, the inflection point, which is where it changes from concave down to concave up, that's right there.
Yeah.
Notice that that is where the first derivative has a local minimum, which means the second derivative must be 0. Remember, the second derivative is merely the derivative of the first derivative. If I wanted to learn calculus and I was going to put one chart on my wall to look at all the time, it would be this one. Because this is very important to understand how functions, first derivatives, and second derivatives are related. But the key thing here is inflection points. Notice that this first function is concave up always on the left side of that inflection point. And it's concave down, and on the right side it's concave up. So the place where it switches is the inflection point, and that's where the second derivative is 0. So in this problem, want to take the second derivative of that function and find out where it's equal to 0. Well, we're going to take the second derivative. Hold on a moment. I forgot we're dealing with a tricky problem here that doesn't tell you what the first function is. Let me look at this for a second. It's a semicircle with f of 0 equal to 5. Find all values of x which the graph of f has an inflection. Oh man. It's a little difficult because notice that if we look at the graph, that's concave up everywhere. And that's concave up everywhere. So I don't see an inflection point anywhere here. Now, I suppose one could make the argument that that might be an inflection point. Do we have answers? Are answers at the back of this?
No, we do not have answers, sadly.
Okay. Unfortunate. Whenever you're learning calculus, you want to always try to have answers, because sometimes when you can't figure out a problem, having the answers allows you to figure out how to do it. And that's why most calculus books will give you answers not just to the odd problems, but to all of them.
Yeah.
Find all values of x at which the graph of f has a point of inflection. Well, the question is 0, 2 an inflection point? Notice that that's a cusp or corner, whatever you want to call it. But when you have a cusp or a corner, the function is not differentiable across that. In other words, this is a continuous function, but it is not smooth. And smooth functions mean they are differentiable across the entire function. Well, we can differentiate this from this point to this point, but we can't differentiate it at 0. It's a cusp. So I'm not real sure what the answer to A is for points of inflection. We have concave up there, concave up there. That can hardly be a point where the second derivative is equal to 0 because the first derivative isn't even defined there. So I'm not sure what they're looking for A. I don't know of any. Find f of minus 4 and f of 4. Okay, 1, 2, 3, 4. What is f of minus 4?
F of minus 4. Well, since this is the derivative of f, would we have to...
No, we're talking... Oh, man. No wonder I'm having problems. There'd be a point of inflection at minus 2. I forgot we were looking at the derivative of the function. The graph they're showing us is not the function. The graph they're showing us is f prime. So if we want points of inflection, it would be where the derivative of this function is equal to 0. Well, right there. And perhaps, I'd have to check my textbook, but perhaps points of inflection are also where the second derivative is equal to undefined. So there might even be a point of inflection here. I don't honestly know. But for sure we have a point of inflection right there at minus 2, 0. The reason being is that the first derivative of this is the slope, and that slope is going to be 0. So the second derivative of the function is going to be equal to 0 right here at x minus 2. And it's going to be undefined here at x minus 0, and I'm not quite sure what that means. So the answer to A is either minus 2 or minus 2 and 0.
Okay.
All right. F of minus 4 and F of 4. Wow. So the thing we have to figure out is what the original function looks like. Well, let's see if we can work backwards. We know that f prime of x equals that circle. Well, the equation of that circle is, x minus 2 squared plus x plus 2 squared plus y minus 2 squared equals the radius squared, which is 4. So that is the equation of that circle that has a center at minus 2 plus 2. From your conic sections, that's the equation. Oh man, and that's the first derivative.
So then you'd have to integrate that?
That means what? It means, well, and it's only the bottom half of that circle, which is the negative solution. Let's solve this equation for y. Can we even do that? Yeah, I guess we can. Y minus 2 squared equals 4 minus x plus 2 squared. Take the square root of both sides. Add 2. So now, plus or minus, but clearly we're dealing with the minus side. Even though it's above the y-axis. It's above the y-axis because of this plus 2. So really what we have is the minus square root of 4 minus x plus 2 squared plus 2. So that is the equation of the first derivative. In other words, f prime of x is equal to this between minus 4 and 0. So we need to integrate this. If dy dx is equal to this, then dy equals that whole thing times dx. You with me so far?
Yes.
Okay. Integrating both sides, we get the integral of this equals the integral of that. Well, the integral of that is y equals the integral of this whole monstrosity here, which is minus 4 minus x plus, this is a calculator problem, so we could figure this out on the calculator.
plug all that in.
That is what y, the original function, is going to be. Now, so once we come up with the original function, let me look at that for a second. Is there an easy way to do that integral? That doesn't look like a particularly easy integral to do. Notice that, no. Why would they give us such a tough integral to do? Are you good at the NINT?
At the nin?
The thing, yeah, in other words, solving integrals from your calculator as opposed to doing them manually.
No, I've never been shown how to solve integrals in my calculator.
Okay, let me show you how to do it. What, you have a TI-84?
Yes, I do.
Slightly different, but let's say the differences are easy to do. Let's say I wanted to integrate x squared from 1 to 2. Well, I would take NINT. Do you know how to find that on your calculator? I think you look on math. If you have a TI-84, you go to math functions and go to 9, I think, which is numerical integral.
Okay.
And then you put in parentheses, like I've done here, and then x squared. And on your calculator, you do it this way, comma x, comma 1, comma 2, in parentheses, like that. And that would give you the value of the integral of that function evaluated from 1 to 2. And that function can be as complicated as you want it to be. On Wolfram alpha, I don't need to define the variable of integration, so I put it in like that. And once again, the beauty of Wolfram alpha is it gives you feedback. So it tells you exactly what we're looking at. In other words, did I put it in correctly? Yes, because I'm looking for the integral of x squared from 1 to 2 dx. They're telling me it's 7 over 3. They even tell us that the area under that curve is 2.33. Gives you a left sum. Wolfram alpha is really quite good. Plus c. So it's worth you knowing how to do NINT on your calculator, particularly when you're doing problems like this where the calculator is allowed. And we're dealing with very complicated functions. I'm not sure yet how to solve this. And looking at it, it looks like some sort of an inverse trig function. On the other hand, it could be just simple substitution to solve it, but it still looks quite difficult to solve. Let's see, if I square that bottom, I'm going to get an x squared, and I don't have an x. That's really going to be tough. Not sure how to do that one manually. You might have to have a calculator to do it. And I could put it into Wolfram alpha and get an answer that involves a plus c because it's an indefinite integral. So, which tells me that I'm not sure how I'm going to find f of minus 4. Excuse me. Ooh. Allergy attack. Let's see. They tell me that f of 0 equals 5. Alright, that's going to let me solve for f of minus 4. In other words, up here, this piece of information, f of 0 equals 5, means that when I solve this differential equation, notice that what I really have is dy dx equals minus 4 minus x plus 2 squared plus 2. There's my differential equation. So I'm going to separate the variables and then integrate both sides. Well, one thing I can do right away is take the 4 plus 2 and make that 6. Yeah, I hope I didn't lose a sign here. Now, it's really not as tough as I thought. Let's solve for dy. dy equals this whole thing, which is minus 6 plus x plus 2 squared. Let's square that. So we get x squared plus 4x plus 4. And I am subtracting that whole thing. And this is all dx. You see where we're going with this? We're going to actually be able to solve this by hand. It looks like, if I'm not mistaken, that dy equals x squared plus 4x minus 2 dx. Can you solve that differential equation?
Okay.
In other words, last week's session was all about solving these. If I could separate the variables, then I could solve it by integrating both sides. So what's my next step here?
The next step, now that we have dy dx, would that be just simply to integrate the different parts of it?
Yeah. So when we integrate both sides, I get y equals x cubed over 3 plus 2x squared minus 2x plus c. You see that?
Yeah.
How I got that?
Yeah.
Right. Now they tell us that this initial condition, usually differential equations, particularly like this, I'm not an expert on differential equations, but I understand differential equations where you can separate the variables. They always include an initial condition, and they told us that the initial condition on the semicircle, the left side of this graph, is that f of 0 equals 5. Well, that means y is equal to 5 when x equals 0. Telling me that c equals 5. In other words, the initial condition on a differential equation allows you to figure out c. Okay, so I'm going to go back up into my, this is the original function. At least from minus 4 to 0. Now, if I want to know what f of minus 4 is, I plug it in for x. If I want to know what f of 4 is, I plug it in for x. Whatever y comes out to be, that's what f of minus 4 and f of 4 are. Do we need answers here? Is this a test that you have to turn in, or is this just a practice test for preparing for the Calc AB test?
I think she wants to see that I've done work with it, but I don't think I need specific answers.
Okay. Then let's, since each one of these questions looks like it's liable to be a half-hour problem, let's stop the exercise, at least question A. Well, no, we still haven't fully answered question A. We've answered A and B. Let's look at C. Now,
C
is actually pretty easy, I think. Yeah, it actually is. Let's talk about that. Let's go back to this. If I'm looking at this original function, there is an absolute maximum right there. Why? Because it's concave down, and the slope of the tangent line is 0, which indicates a maximum or a minimum, but the fact that it's concave down indicates a maximum. Over here, the slope of the tangent line is also equal to 0. So I know that these two 0 points right there indicate a local maximum or a local minimum of the original function, but I don't know which from just looking at that. But there's something called the second derivative test, where if you take the second derivative of the function, notice that it's negative there. In other words, if I go all the way down to the second derivative, I'm in negative territory. So if the second derivative is negative, it indicates concave down, which means it's a maximum. If the second derivative is positive, it means it's concave up, which means it would be a minimum. So the way to memorize it, or at least the way I've memorized it, is second derivative negative, concave down, negative goes with down, second derivative positive, concave up, up goes with plus.
That makes sense.
So question C, find the value of x at which f has an absolute maximum. Well, if we can take the derivative of this function and find out where it is negative, that will be where the absolute maximum is. And we have to take the derivative of the derivative, because we're talking the second derivative of the function. So I suppose I could start with that function, but that's just the function to the left of the y-axis. We haven't even gotten to doing, looking at the function to the right of the y-axis. In other words, when x is 0 to 4, the function's entirely different. It's 5e to the minus x over 3 minus 3. Okay, so, oh man, that means I screwed up b. Because to find f of minus 4, I used that right there. That was correct. But to find f of 4, we're talking about an entirely different original function. In other words, to find f of 4, I have to take the derivative, the integral of that function there. Solve for the c. No, I don't have to solve for the c, because the f of 0 equals 5 applies only to the g of x. So when I integrate this, wow. Because it's an exponential function, the integral is not going to be plus some c, it's going to be c times e to some function. Which means not sure what that means, but when we go to calculate f of 4, we have to know what that original function is. I don't see how we're going to calculate the c on that original function. Well, let's see. To the left side of this equation, in other words, with the semicircle only, we should be able to figure out where the maximum occurs. It's hold on a second, I'm thinking. This is the derivative function. That's that semicircle. Pretty much, half of it at least. The lower half. So if I implicitly differentiate this, I will get the second derivative, and I can check where the second derivative is less than 0, and that will be an absolute maximum. And clearly it's going to be at 2, minus 2 rather, because the first derivative of this is what I want to set equal to 0, and that's only one spot right here, or undefined, so it potentially could be there. Because the derivative right there of the left side is undefined. So those are two possibilities for local maximums. So if I take the second derivative, and check these 2 points, I'll tell which one of them is a maximum and which one maybe is a minimum. These seem awfully complex today.
Yeah.
Don't you agree?
Yes, they do.
Okay, if I implicitly now let's combine it. Let's see. And I implicitly differentiate this. I get, to solve for dy dx, I get 2x plus 4 plus 2y prime minus 4y prime equals 0. I solve that for y prime, I get minus 2x minus 4 divided by 2y minus 4. So this is the second derivative of our original function, at least to the left of the y-axis. So the question is where is that negative? Is it at minus 2? If I plug in minus 2 for this, do I get a negative answer? Oh man, what do I plug in for y? When I plug in minus 2, I get 0 in the numerator. I do not get a negative answer, regardless of what y is. What if I plug in 0? Because the other critical point here is that one right there. That's where the second derivative is undefined. Here's the second derivative, so if I plug in x equals 0, I'm going to get a minus 4 over 2y minus 4. Without knowing why. A better way to solve this would be not to implicitly differentiate it, but to explicitly differentiate it. Wow. This has gotten so complicated I'm completely lost. You know what? Let's go to the next problem.
Yeah.
Just, this one's giving me a headache.
It is very confusing. They seem quite challenging to do for some reason.
Very, very challenging. Let's see. All of these, oh, I see. This is just, why, boy, they're giving you the free response. Aren't the free response the toughest questions on the test? Aren't they like
so.
extra credit bonus questions? So this page here is the free response question from the 2009, the 2008, and the 2010, and the 2005 and 7 AP tests. So what we're looking at here is the 7 toughest questions over the last 7 years of AP tests.
Yeah.
Which I don't mind doing, but when you're giving me this tough of material, I really would appreciate if you can send it in advance. I understand you didn't get it in time, and I'm happy to do this without preparation and just kind of take it as good as I can do it. Well, let's have a look at it. It's going to be challenging, but maybe there's something to be learned from it. Also, maybe not. I tend to think that these have limited usefulness when you're trying to... this is like taking a skier who is brand new and throwing them on the expert slopes instead of starting them out on the beginner slopes.
I think that skier might hit a tree or something.
Yeah. It just kind of is demoralizing when you run into calculus problems that are so hard that you just have no clue. What's the point of that? I don't know. Let's have a look at this. Okay. So they're telling us that the original function is twice differentiable, which is useful. That means we're going to be able to calculate stuff like inflection points and things like that. In other words, we can calculate rate of change and the rate of the rate of change. Use the data in the table to estimate the rate at which the number of people waiting in line was changing at 5:30. Show the computations that lead to your answer, indicate units of measure. This is when t equals 5.5. The number of people waiting in line was changing by what? At 5.5. Clearly halfway between this. Question is, can we use halfway between the function? Let's draw this function. T is going to be that. Now remember, this is the original function. This is not the rate of change. So it goes from, let's see, from a low of 0 to a high of, we'll call that 200. So it's at 0, we start with that point. At 1, we go up to that point. At 3, we go to about there. No, not quite that high. At 4, we go back down to 126, right about there. At, let's see, we're going to 9. And this is 4. So 7 is 150. 8 is 80. And 9 is back to 0. So, we don't have a continuous function. We have a collection of points.
Yeah.
But they're asking about the rate of change that's going on right there. Well, clearly that rate of change is the slope of that line. It can't be anything else. We can, at best, connect those two dots with a straight line. So it's that slope is the rate of change at 5:30. And in fact, the rate of change at any point between 4 o'clock and 7 o'clock is that. What is that slope?
That, it looks like a linear slope.
Yep. Has to be linear,
yeah,
because they only gave us points and we can't
Yeah.
estimate the curve between those points. So it has to be, have to assume it's linear.
So we have there, that's the dots between 4 and 7. So that's 150, 24 over 3. Is that 8?
It is. So, what does that tell us? The number of people waiting in line was changing at 8 people per hour, which makes sense. In other words, you don't go from 126 to 150 without increasing. And the rate is, if we added 8 people every hour in line, then we would have 126 at 4 o'clock, 150 at 7 o'clock. So that slope makes sense. And the rate of change is 8 people per hour for A.
So then, since we're estimating what it is at 5.5, would we take the value at 4 and add 12 to it?
No. What we did was we took our original function, which was a collection of these points, and we found the rate of change. Let's say that this, let me go ahead and connect all these dots.
Well, yeah, okay, so I guess what I was trying to get at then is if the rate of change over every hour is 8 from 4 to 7, and we're trying to find what the value is at 5.5, then wouldn't we take the rate of change plus half the rate of change to get to how much it's changed in the hour and a half?
Well, first of all, the rate of change for that entire time period is the same.
Yeah.
In other words, at 1 minute after 4, the rate of change is 8 people per hour are being added to the line. At 1 minute before 7, the rate of change is 8 people being added to that line every hour. So at 5:30, it's just 8. That is the rate of change. They don't want the number of people in the line, notice. Use the data in the table to estimate the rate at which the number of people waiting in the line was changing. They haven't
thought
asked
they
us
wanted-
yet how many people
Yeah.
were in the line.
I thought they were asking for the number of people. I guess I didn't read the
No,
question
they're
well
not.
enough.
If they were, we would take 12 and add it to 126. Okay?
Yeah,
And
that's what my
if they said what was the rate of change at 2 o'clock, it's the slope of that line. In other words, because we don't have a curved function here, the rate of change is just the slope of the linear lines that connect each of these dots, instead of the slope of the tangent to a curve, which is the normal rate of change. I mean, in calculus. All right, let's look at B. Using a trapezoidal sum with 3 intervals, estimate the average number of people waiting in line during the first 4 hours that tickets were on sale. Okay. With 3 intervals. Well, that's convenient. That means that one, and that one. There's interval 1, there's interval 2, there's interval 3. Now, well, this is actually pretty easy because we know this is 120. We know this is 156. We know this is 176. And we know this fourth point is 126. So what they're saying is the average number of people in line during the first 4 hours is going to be what's the formula for average value?
The formula for the average value is the integration of the 1/2 b minus a and then a.
Not one half. 1 over
one
b
over,
minus
sorry.
a
Yeah,
times the area under the curve.
Integration equation.
So if I want the average value between 1 and 4 hours, I want the average number of people, then I'm going to find the area under the curve, and I'm going to divide it by 1 over b minus a, and b minus a is 4. So it's 1/4 of the area under the curve. Well, this area is the sum of 3 trapezoids. So let's look at trapezoid number 1. You've had the trapezoidal method, I gather?
I believe so.
Okay. So how do you figure the area of that trapezoid number 1? Has a height, this side is 156, this side is 120, and that side is 1.
So you solve for the area of the trapezoid
Usually trapezoids are going to be drawn like
and
this.
the area of, or the formula for the
That's the way you'll typically find a trapezoid drawn. Notice that this has been rotated 90 degrees.
Yes.
So the area of the trapezoid is not the base times height, because you got 2 different bases. You got a base 1 and you have a base 2.
Yes.
So it's the average
A
base.
plus b over 2.
1/2 B1 plus B2 times height. That's the function for area of a trapezoid. Well, in this case, this is B1. This is B2. So what's the area of that trapezoid?
130.
130, no, 1, 3618, 138 is the average base. So the area equals 138. Area of 1 equals 138. What's the area of 2 equal?
The area of 2, where our sides are 156 and the other side is 176, right?
So the average base is 166.
And then since it's times 1.
Times
right?
2 on this.
Times 2 there, yes. Then it's 332.
And what's the area of the third trapezoid?
That's got the one side at 176, and then the other side is down to 126.
So the average base must be 151.
Which is what the area becomes.
Since its height is 1. Okay, so what is the sum of those three numbers? Looks like 621 maybe?
Yeah.
Okay. And we need to multiply the area under the curve times 1 over b minus a, which is 1/4. So there is your average value. In other words, there is going to be some value. Let's get rid of everything that I've drawn here. I want to get rid of that or that. Notice that whenever you have a curve, whether it's straight lines or not, there is going to be some value that represents an average value for all of these values. That's what the average value formula says, is that if you take the entire area under this curve or straight lined object and divide it by 1 over b minus a, you'll get the average value. Well, this average value looks to be about 150 something. 155 1/4. 155 1/4. So right about there, if I were to draw a line through that, that would represent the average L of t. Well, over the first 4 hours only, not for the whole thing. If we'd have integrated the whole thing from 0 to 9, then we would have had the average value over the whole thing. But that's the way average value works. Is you take the area under the curve, you divide it by b minus a. All right, so that answers B. So there was an average of 155 1/4 people waiting, and that kind of makes sense. If you look at that table, that's certainly a ballpark figure. In other words, we wouldn't have wanted to come up with 200, right? Your answers always have to make sense. For t, what is the fewest number of times at which L prime of t must equal 0? Give a reason for your answer. Okay. What's that going to mean? L prime of t equals 0.
It was, yeah.
Let's assume, hold it, before you go any further, let me enhance your understanding of this. I believe I can do that. If this was a curved function, let me just make it curved. Now, what would it mean to say, how many times is L of t prime equal to 0? That means the slope of this original function has to equal 0. How many places on that curve is that going to occur?
Well, T, 1,
No,
it looks like.
it occurs
No,
right
wherever it
there.
changes, so 1,
We're looking for the slope to be
2,
horizontal.
so that's 1 there, then at 4 is that one,
Yes?
and then 7, and then
Oh, that's it.
that's it. Yeah.
That's it. Okay? And what that question really is saying is how many times does the derivative change direction? Because we had the number of people in line growing through hour 3, and then from hour 3 to 4 it got less, and then it grew again, and then it got less again. So it's really saying is how many times does it change direction? And you don't need it to be curved to see that. In other words, if I erase my curves, which I can't properly put in there because I don't have those values, because all I have is single values, and replace it with a straight line, well, I still can tell how many times it changes direction. Right there, and right there.
Yeah.
What is the fewest number of times? Must equal 0. Well, at least 3. Now, why did they say fewest?
Because since we don't know the values in between, it could possibly hit 0 in between two of those
exactly.
points.
It could have done something like this between hours 1 and 3. So we could have a lot more 0 sloped points than what our data is telling us just because we don't have enough data. But at a bare minimum, we know it changes direction 3 times. Well,
Yeah, which makes sense.
it's 2 o'clock. Shall we? Let me just take a quick look at D.
Yeah.
Notice that D is integration as net change. They're giving us a rate. Whenever they give you a problem with a rate, you know that you're looking at a first derivative. In other words, R of t is a first derivative. They're saying it's a rate. So if I want to find the total number of tickets sold over a given period, I'm going to take the integral of that and integrate it from opening 0 to 3. So I would answer number 3 quite simply by taking the integral of 550 t e to the minus t over 2 dt, and I would go, they want to know how many tickets are sold by 3 o'clock, which is the total number of tickets sold between 0 and 3 o'clock. So it's the, put that into your calculator, you'll get a exact number. Round it to the nearest whole number, and that will be the answer. Remember integration as net change, that expression, because there's a whole lot of integration problems that are based on that, where they give you a rate. In other words, when I give you a velocity function and I say, here's a velocity function, how many miles did you travel in the first 3 hours? You're going to integrate that velocity function from 0 to 3. And that will tell you how many miles you traveled in 3 hours, because I gave you a rate. Velocity is a rate of change. Just like tickets sold is this is a rate. If we want total tickets sold, we have to integrate this over the time period. All right. These are brutal. Well, I will keep this on file and have a look at some of these, and just in case we want to look at this next time, I might be a little more up to speed on it. This is actually a real good document to have. This will go good in my library of documents, because this looks like about as tough as you're going to get on the AP test. All right, Chase. We're back on at 2 o'clock next Saturday.
Yes, we are.
I will talk to you then.
Talk to you then.
Bye-bye.